Alright, so this will be the third lecture in chapter 10 over alcohols and thiols. So in this lecture we'll look at how to synthesize alcohols. So before we do that, so let's review a little bit because we've already looked at several reactions that make alcohols. So these would be reactions from chapter 6. So if you have an alkyl halide and react it with hydroxide, this can do an SN2 reaction. Right, to make that alcohol plus potassium bromide side product. Or in this case with the tertiary alcohol and the weak nucleophile, then you can do an SN1 reaction, so water will replace the chloride. And of course that goes through a carbocation intermediate, so it could potentially rearrange, but not in this case. So you can make alcohols by SN1s and SN2 reactions, and from alkenes, so this will be chapter 8 reactions. We looked at several ways to make alcohols. So in these conditions, adds H and OH, Markovnikov with carbocation. So you have to look out for rearrangement, right? So this would make that alcohol due to carbocation rearrangement. And the oxymercuration, demercurization, right? If you remember, you add H and OH, but it does not make a carbocation, so there's no rearrangement possible. But it is still Markovnikov addition, so you would make that product. And if you did the hydroboration oxidation, that's anti-Markovnikov, so adds H and OH across the double bond with the hydrogen going to the carbon with the most number of hydrogens. So 3 more ways to make alcohols there. And then we looked at how you can make diols from alkenes as well, right? So if you remember the reagents there, osmium tetroxide followed by H2S would be one way, or you could use cold KMNO4. So that makes, 7 ways so far? You've seen 7 ways to make alcohols so far, so this should give you some idea of the importance of alcohols. So alcohols are very important in organic chemistry. So organic chemists have lots of tools in their toolbox how to make alcohols. So they're important in organic chemistry, very important in biological chemistry as well. So this is just some examples from biological chemistry. So this molecule with the phenol is called tyrosine. So that's one of the 20 common amino acids. This is another amino acid with an alcohol. So this one's called serine. Here you have a secondary alcohol. This one's called threonine. So you see alcohols all over the place in amino acids and peptide protein chemistry. Sugars have lots of alcohols in them. You see thiols as well. So this is another amino acid. This one's called cysteine. So you see thiols in protein chemistry. You see alcohols used in medicine, right? Simple molecule like isopropyl alcohol is an antiseptic, disinfectant, has antimicrobial and antivirus properties, right? 70% solution of isopropyl alcohol will kill the coronavirus on surfaces within 30 seconds. So you see alcohols all over the place in biological chemistry, organic chemistry. So this will be one of the reasons why chemists have a big interest in being able to synthesize alcohols, because they do have so much utility. So in this chapter, we'll look at some new ways to synthesize alcohols. So we're using what are called organometallic reagents. So this will be, organometallic reagent means you have, so organo mean carbon attached to a metal. So like this would be an example. So this would be an organolithium reagent. So you can have any R group or any R group, alkyl group, attached to magnesium, which also has a halogen attached. Those are called organomagnesium reagents, or specifically they're called Grignard reagents, named after Victor Grignard, the chemist who discovered them, who went on to win a Nobel Prize in 1912 for his work. Okay, so what is the significance of organometallic reagents? Well, so carbon has electronegativity of 2.5, and lithium is 1.0, and magnesium is 1.3, so carbon is more electronegative than lithium and magnesium. So that means carbon is partial negative, right? And magnesium is positive, or carbon's negative and lithium is positive. So that is significant because carbon is usually attached to something like fluorine, chlorine, bromine, iodine, nitrogen, or oxygen that are each more electronegative than carbon. So in these cases, carbon is partial positive. So if you take something that's partial negative with something that's partial positive, carbon negative will react with carbon positive. So you can use them to make carbon-carbon bonds, and that is their significance, right? Anytime you can make a carbon-carbon bond, that's important in organic chemistry because you can take a simple molecule and you can make it much more complex. So just a few words about their nomenclature. So like this one, you just take the alkyl group and then lithium. So cyclohexylithium would be the name of that. Or in this case, the alkyl group. And then magnesium, and then the halogen as a halide. So fluorine would become fluoride, chlorine, chloride, bromine, bromide, iodine would become iodide. Okay, so how to synthesize these things. So the mechanism's fairly complex, so we're not going to go through the details of the mechanism. We're just going to keep track of electrons. So we're just going to do some bookkeeping to keep track of electrons to show you that the electrons work out. So if you take so you start with an alkyl halide in both cases. And if you react that with magnesium, magnesium's got 2 valence electrons, right? So let's do this. First of all, let's split the carbon-halogen bond and let carbon and bromine take its electron back. And then let's give one of the electrons from magnesium to bromine. So bromine had 3 lone pairs to begin with, now it has 4, so now it's Br minus. And then magnesium's got 1 electron left, and carbon's got 1 electron, so let's let those 2 make a bond to give you this. And then let's let bromine attach to magnesium, so you would make the organometallic reagent, where now carbon has a partial negative charge to it. Okay, so one important point to make here is the solvent must be aprotic. That means it has to be non-protic, right? You cannot have a partial positive hydrogen on it. So why? So the solvent must be dry, so that you can't have any water present. Why? Well, carbon's partial negative, hydrogen's partial positive in water. So if you put a positive and a negative together, they're going to react. So in this case, we would take these 2 electrons and make a bond from carbon to hydrogen. And these 2 electrons in the OH bond would become a lone pair on oxygen. So that carbon, of course, already has 1 hydrogen, now it's got 2. So you basically destroy. If there's water present, it will destroy the Grignard reagent. And then you would make this magnesium salt. So you can't have water present. So your solvent has to be dry, and it can't be a protic solvent. Well, like in alcohols, right? That's protic. Well, this carbon's partial negative, so that carbon would just take this hydrogen, and you would make propane. Right? That was a CH2. Picks up a hydrogen, now it's a CH3, so you made propane. So you would destroy your Grignard reagent. So you can't have protic solvents, you can't have water present. And so then a common solvent for making organometallic reagents would be using something like ether. So there's another problem if water's present. So you're just adding chunks of magnesium, either as magnesium strips or small pieces of that magnesium to your reaction. And magnesium can react with water itself. So it will react to make magnesium hydroxide and hydrogen gas. And since your solvent is ether, well, magnesium hydroxide is not soluble in ether. So what it's going to do, it's going to coat. It'll coat the surface of your magnesium. And once that surface is coated, then the magnesium can't react anymore. It can't react with your alkyl halide to make the Grignard reaction. So that would stop that reaction, and you're not going to make very much Grignard reagent. And any Grignard reagent that you do make would react with water and be destroyed. So you got to use dry aprotic solvents. So solvents that are typically used would be diethyl ether. So diethyl ether, if a chemist ever says ether, they're probably talking about this compound, which is diethyl ether. Or they would use this solvent called THF, which is just a cyclic ether. So THF is just an acronym for tetrahydrofuran. So they're both aprotic solvents. They're both polar. THF being more polar than ether is, but they're both aprotic. So you make organolithium reagents the same way. So it's a complex mechanism. So let's just bookkeep the electrons. So you need 2 moles of lithium for every 1 mole of alkyl halide. So let's just split this. Let's give carbon and chlorine their bonds back, their electrons back. So then one of the lithiums can attach to carbon to make the organolithium reagent using those 2 electrons, and lithium has 1 valence electron. So it can give up 1 to chloride, and then you would make a Li plus cation and Cl minus anion, so lithium chloride side product. Okay, so yeah, so that's, so if you ever see that, so alkyl halide with lithium with ether solvent, you're just going to make organolithium reagent. Okay, so now what reactions do they undergo? So very commonly, so it's very common to react them with a compound that's got C double bond O, because in this case, so carbon is partial positive because oxygen's more electronegative, and carbon's partial negative there since carbon's more electronegative than magnesium. So basically what happens is you take those 2 electrons and you make a bond from carbon to carbon. That would put 5 bonds on carbon. You can't put 5 bonds on carbon, so you have to break a bond. The weakest bond is the pi bond. So we're going to break the C double bond O, one of those bonds. And the pi electrons are going to become a lone pair on oxygen, so now oxygen's got 3 lone pairs because it had 2 to begin with. And whatever the R group is attached to magnesium, you just stick it on the carbon of the carbon-oxygen double bond. So the oxygen's now negative. You took the electrons from magnesium, so magnesium's positive, so you have this salt after the first step. And then that's waiting for you to do the second step, so now you add an acid. So oxygen that's negative can take this hydrogen that's partial positive. And that's your major organic product. And then your side product in this case would be magnesium chloride. Okay, so this aldehyde is known as formaldehyde. So if you take an organolithium or organomagnesium reagent with formaldehyde, then you make a primary alcohol. So it's a similar reaction if you react with an aldehyde. So that's partial negative, that carbon's partial positive. So whatever's attached to the magnesium, you're going to stick on that carbon and break the C double bond O. That will become an O minus. And then the second step, so you see a variety of things wrote for the second step. It could be H2O, HCl. It could just be H plus that's wrote on the arrow. So organic chemists are notorious for just putting not the entire reagent there, just basically what's needed, which is the H plus, and the H plus is coming from something like HCl, for example. Or you may see H3O plus used. Again, it's all just a source of hydrogen, H plus. So you do the second step, O minus, picks up an H+, and now you have an alcohol. So starting with an aldehyde, in this case you made a secondary alcohol, right? Because the aldehyde already had one carbon attached, and then you added a second carbon from the Grignard reagent. So it's going to become secondary. Why do I have this road here? I don't know why I have that road. Same thing. Let's get rid of this. Okay, so if we did this reaction, so an organolithium reagent with a ketone in this case, it's the same basic reaction. This carbon's partial negative, that one's partial positive. So whatever's attached here, we're going to take the 2 electrons in the carbon-lithium bond and use to make a bond to that carbon, and they're going to break the C double bond O. So now that's negative. And in this case, H3O plus was the reagent. But again, it's just a source of hydrogen. Oops. So you're going to take a lone pair on oxygen, make a bond to hydrogen, and that's going to become a water molecule. So from the ketone, then you made a tertiary alcohol. So Grignard reactions, organolithium reactions, you can make primary alcohols, secondary alcohols, tertiary alcohols. Just depends on what you reacted with. Formaldehyde, primary alcohol, aldehyde, secondary alcohol, ketone, since it's already got 2 alkyl groups attached to that carbon, and then you're adding a third, it's going to become a tertiary alcohol. Okay, so if that made sense, then see if you can predict the product. So if you take these 2 reactions and see if you can predict their products. Okay, so what happens in this reaction? So again, we're just going to take whatever's attached to magnesium, stick it there, and this is going to become an OH. Right, that would be your product, tertiary alcohol. And so again, if you're thinking about the mechanism, that attacks here, that becomes an O-, and then that picks up a H in the second step. Okay, so in all of these reactions, I've been writing the Grignard reagent or organolithium reagent on the left and the ketone on the arrow, but it doesn't matter. You can put the ketone here and the organolithium or organomagnesium reagent here. It's just the same concept. Whatever's attached to magnesium, you're going to attack here, and that's going to become an OH after it picks up a hydrogen in the second step. So C double bond O becomes an OH, and whatever's attached to magnesium or lithium, you attach to the carbon that was a C double bond O. So that would be your product. In this case, you started with an aldehyde, and you made a secondary alcohol. Okay, so if we predict the products here, we're going to take that, stick that here, and that's going to become an OH. And that would be your product, right? Okay, so some subtle things to notice here. So there's some language here that to recognize. So this 1 and 2, what does that mean? So that is information to a chemist. What that means, it means do step 1. After step 1, reaction is done. And then do step 2. So that means you take the Grignard reagent and the ketone, let those two react with each other. After that reaction is done, then you add the H2OH plus. If you write it like this, what does that mean to a chemist? That means add everything at the same time. And you're going to get very different results because of that. So if you did the first reaction, then you get what you expect. Right, that would be your product. If you did the second reaction, then what you get is an explosion. Why? Well, because this is partial negative, so that is partial positive. So if it reacted as a nucleophile, it would react there. So if the Grignard reacted as a nucleophile, it would react there, but it can act as a base as well. And it's going to react as a base before it reacts as a nucleophile. So since you have an acidic hydrogen present, then that's what would happen. This would just take that hydrogen and you would make benzene. And that's a very exothermic reaction that would generate a lot of heat and could potentially cause this reaction to explode depending on the quantities of material involved. So number 1 and number 2 is information to a chemist. It tells the chemist the sequence of order to add things. And if you don't have those numbers together, if the chemist doesn't know what well, a chemist would know what they're doing, but somebody who didn't and is just following the recipe, to them that would mean add everything to the same flask at the same time and you have a problem, right? So if you forget to put 1 and 2 in on your arrows and you're doing a synthesis, I'll take off a few points for that because that's information that you should know needs to be included. Okay, so a few more reactions of Grignard reagents and organolithium reagents. So if you reacted with an epoxide, well, that carbon is partial positive and that carbon is partial positive and that carbon is partial negative, so it could react with either partial positive carbon, and of course they're symmetric, so it doesn't matter which one. But that's going to react here and that's going to open up the epoxide ring. So now the Grignard reagent, organolithium reagent is attached 1 carbon away from the C double bond O. Whereas in all of these examples, it ends up attached to the carbon that had the OH on it. Here it ends up attached 1 carbon away from the carbon with the oxygen on it. So that's what you get after the first step, and then you do the second step, H+. So then you just pick up a hydrogen on that carbon. And that would be your product. Okay, and if you react with an ester, then the reaction's a little bit more complex. So again, that's negative, that carbon's positive, so those are the 2 carbons that are going to react with each other. So this is going to attack there and break the C double bond O, just like you would do in all of the other reactions. But then the common mistake that students make all the time is stick hydrogen on at this point. So do your second step. So that's the common mistake students make because that is not the product. That is not what happens with an ester. So you do make this in your first step. But then what happens is you have a leaving group on that carbon. So you can remake your C double bond O and the OR group of the ester can leave. Let's put these double bonds in the right spot. Okay, so now you have that. So the OR group left took those electrons with it. Right, the oxygen had 2 lone pairs to begin with, now it has 3, so it's O-. But now you made a ketone, and ketones react with Grignard reagents. So as you, or an organolithium reagent. So as soon as you made this, it would react again. So another equivalent reacts. Makes O minus again. And you still have this floating around in solution. Right? So if you have an ester, you add 2 equivalents of the organolithium reagent or the organomagnesium reagent. So that's what you get after the first step. And now it's waiting for you to do the second step. So since you have 2 O minuses, technically you need 2 equivalents of H plus. So O minus picks up hydrogen, and this O minus picks up a hydrogen, and you would make those 2 alcohols. Okay, so let's try to make this easier to just see the product. So if you're reacting an ester with an organometallic reagent, so it could be RMGX or it could be RLI, doesn't matter. Basically what's going to happen is 2 of these are going to add here, and that's going to become an OH, and this is going to break off the molecule. So you add 2 R groups here, and whatever the OR group is comes off the molecule. So you would make that as your major organic product, and of course this is organic as well. Okay, so if we take that, and this is a little bit similar example, but a little bit more complex. So this is an ester. It's a cyclic ester, which is called a lactone. Okay, so organic chemists are notorious about not balancing reactions. So technically you need 2 equivalents of this, but it may not be shown like that. Not 2 equivalents of that. Technically you need 2 equivalents of this. But organic chemists are notorious for not balancing chemical equations. It's just understood. You understand what's going to happen when these 2 things react with each other, so that you can predict that that's your major product. So same thing here. So maybe I show 2 equivalents here to try to clue you in, or maybe I just expect you to recognize that you need 2 equivalents of that. So what's going to happen here, first of all, one of these is going to attack here and make that a C11O, or CO minus. All right, but then you're going to remake the double bond, and the OR group is going to leave, but it's going to remain tethered to the molecule because of these carbons. All right, so now you have that. Now you have a ketone, and that reaction happens again. So another equivalent comes in. Makes that an O minus again. Now you have 2 of the R groups added there. And you have 2 O minuses, just like you had 2 O minuses here. And now that's done with the first step, so now you have the second step, and again you would need 2 equivalents of H plus since you have 2 O minuses. So pick up a hydrogen there, pick up a hydrogen there, and your product would be that diol. Okay, so acid chlorides react similarly to esters. So this is going to come in there. You're going to break that. And then you're going to remake the C11O and kick off a chlorine. And then another Grignard reaction is going to react. So that's going to attack there. You're going to make that an O- again. Now you've got two of these added there, and that's what you have after the first step. And now you're going to do the second step, and O- is going to pick up a hydrogen. And that's your product. Okay, so sometimes you see organolithium, organomagnesium reagents reacted with D2O. So if you remember, what is deuterium? It's just an isotope of hydrogen, so that's a partial positive D. So that carbon is partial negative. So you can take these two electrons and make a bond to deuterium. And so that would be a way to introduce deuterium into your molecule. And then your side product is DO- and MgI+. So that's salt. Okay, so this problem. So carbon's partial negative, and that carbon's partial positive, right? And if the Grignard reagent acts as a nucleophile, right, then it goes there. But we made the point before is that you can't put Grignard reagents or organolithium reagents in the presence of acidic hydrogens, of protic hydrogens, like that one, because that's partial positive. And if this acts as acid base, then it's just going to take that hydrogen, and it's always going to act as a base before it acts as a nucleophile. So that's what's going to happen in this reaction. You would just destroy the Grignard reagent. It would just take off a hydrogen from that molecule, from the OH, and be done. And you would make benzene, and the aldehyde didn't react. So that's just an expensive base that you use to deprotonate an alcohol if that's what happens. If you wanted it to react at the aldehyde, then you would need two equivalents of the Grignard reagent. The first one's going to act as a base and take off a hydrogen, and then if you had more Grignard reagent present, then it could react at the aldehyde. Okay, so lastly, so we looked at several reactions now of Grignard reagents. So let's do a synthesis problem. So let's take this tertiary alcohol and let's synthesize it by three different Grignard reactions. Okay, so the thing to recognize here is that we could have made this bond, so we'll call that A. Or we could have made this bond, so we'll call that B. Or we could have made, let's see, what do we need? We could have made this bond, so we'll call that C. So we could have unzipped this molecule three different ways and made it from three different ketones and three different Grignard reagents. So if we undo bond A, then this would have been your Grignard reagent, and then your alkyl, then your ketone would have been that, right? You would have had a methyl from, you would have that methyl and the propyl group attached to it. So you'd react it with this Grignard reagent and then 2H+, and you would make that alcohol, right? Because this would go here, and that would become O-, which picks up a hydrogen in the second step. Or if we undid bond B, then that could have been your Grignard reagent. In the first step and the second step, H+, and then your ketone would have had, so the old alcohol started out as a ketone, C double bond O, and it would have had a methyl group attached to it. And a benzene attached to it. All right, so in this case, then if this attacked there and that became an OH, you would make this tertiary alcohol. Or we could have undid bond C, and CH3 could have been your Grignard reagent. In the first step and the second step, H+, and then you would have started with a ketone that's got a propyl group and a benzene group attached to it, right? So if you did this reaction, then the CH3 would attack here, and that C double bond O would become an OH after the picks up a proton in the second step. Okay, we'll stop there.